You ready? Hello, everyone. For those of you that don't know me, I'm Victor Barocas. My primary employment is in biomedical engineering, but I also have graduate advising privileges in mechanical engineering, so I have various involvements with the program over the years. So one of the things I did was I introduced some of the mechanical engineering people, my old friend Asan here, who is going to be our speaker. Is Aman. I first met him when he was a graduate student at RPI studying fiber network mechanics. And I then sort of continued to know him as he moved to the University of Pennsylvania, where he did some more work on fiber mechanics and cell matrix interactions. And subsequently, he moved to Yale, where he worked with Jay Humphrey, looking at vascular remodeling and cardiovascular mechanics. About a year ago, you said, he moved here to work at Medtronic. So he's really seen a wide range of things, from the extremely idealized and theoretical up to the very practical. And I think you'll enjoy hearing what he has to say. I think he's going to talk mostly about his work from his postdoc and then a little bit about Medtronic.
Few slides.
Excellent. So with that, Asan.
Thanks for the kind introduction, Victor. I'm really glad to be here today, and I have some material from my postdoc work, mostly at Yale in Jay's lab. I hope that I can entertain you with presenting the research on aortic dissection and modeling some surgeries, collaborative work that we did. So I'm gonna go right to it. I'll talk about computational modeling of tear propagation in aortic dissections, and how we can model that using phase field modeling. What is the critical pressure that would drive a tear to move in the wall of the vasculature? I will look at some of our collaboration with surgeons on if they see a CT scan, when is a good time to operate, if the aorta is getting larger, how large is too large. That's the work on Laplace law here. And then there's another application of computation in biomedicine. I will look at a model of forming a connection or attachment between a graft and the native vasculature. So how can we model that and see how the tissue would be connected to a polymer graft? And then at the end, I will talk about, I have put a few slides on the work that I've been doing in the past year in Medtronic. And I'm really here today hoping that I can connect with the local experts and also students, because we always need fresh engineers at Medtronic. So it would be good if I can get in touch with you, with students, and I'd be glad if I can help. So I'll start with talking about aortic dissections. It's aortic dissection is a disease of the aorta that can be deadly. And in this disease, blood coming from the heart going into the aorta would get in between the layers of the aorta. And then the lamination of the aorta can progress. As shown here, the layers can become separated, and it can go down all the way to like near the kidneys and downstream parts of the body. And when this happens, the blood would be diverted away from where it's supposed to be, and that can be a deadly situation. Usually when a physician looks at that, the physician would see that instead of the true lumen where blood is supposed to be, there's another false lumen where blood is flowing in, and then instead of going to the organs, it's being stuck there. So that organs downstream would not receive the oxygenated blood that they needed. So it would cause a disease condition. And immunological staining and histology has shown that when this disease happens, there's accumulation of glycosaminoglycans, proteoglycans inside the vessel wall. So these are highly negatively charged molecules that would imbibe a lot of water, and that creates some pressure. And my lab at the time hypothesized that this could be one of the mechanisms by which the initial nucleation for this tear to form occurs is by this imbibing of water around these proteoglycans. So we had some questions about the mechanistics underlying this disease. Is that how can we reach a critical pressure that would cause this delamination to happen? Could it come from these glycosaminoglycans? Could it come from blood pressure? And then the progression, how can we model that? And then why would delamination happen versus rupture? We went to some historic good experiments from a lab in Canada, from Margot Roach, who recently, unfortunately, passed away. In these experiments, they took a piece of aortic tissue, laid it flat on a tabletop, and inserted the tip of a needle in between the layers of the aortic wall. And they injected fluid and measured the infused volume. They were injecting black India ink, and they measured the fluid pressure by having a pressure transducer in the loop with their tubing. And they reported the critical pressure. What is the pressure when this tearing starts to propagate? And after the tear starts to propagate, the pressure comes down. Before that, all the deformation is elastic. We only inject some ink in between the layers and the tissue would bulge, but the tear would not propagate. So we wanted to see how much is this pressure. It's 70 kilopascals in their experiments, and it's above 400 millimeters of mercury. So if you've seen numbers of blood pressure, it's usually 120 over something. So this is very high, much higher than normal and hypertensive blood pressure. And it makes us think, if it takes this much pressure to delaminate the aorta, why does it even happen? And we wanted to see how does this pressure correlate with the stiffness of the tissue and the strength of the tissue, and then the area of the tissue that is pre-torn. So when they do the experiment, we understand from a fracture mechanics point of view that there's an initial defect. So when we insert the needle into the tissue, we are creating an initial chamber that the ink has to dilate. And so if the tissue degenerates, we would think that the stiffness might come down and the strength of tissue might come down. So we want to explore a little bit what is this functional form like. And then another set of experiments that the Roach group did looked at the propagation of tears and by the injection of ink in the thoracic region of the aorta versus the abdominal region. So the curve that we saw with the critical pressure came from thoracic tissue. And when they looked at abdominal tissue, they saw a different pattern. There was like S-shaped steps, and there was multiple of them as the pressure was increased. So we wanted to look at the mechanism of this in computational modeling. The reason that they reported was that in the thoracic region, there were distinct elastic lamella, but in the abdominal region, these lamella were connected by radially traveling struts in between the layers. So I will present computational modeling that would explore the possibility of getting this kind of S-shaped curves. The computational modeling that I will present is uses phase field modeling. So this is the slide with all the equations for the computational model. So it stems from an energy that has the formation of the wall. So Neo-Hookean part, for people who know it, Neo-Hookean is like how rubber would deform, and exponential stiffening is how usually tissues deform. Like if I pull on my earlobe, like in the beginning it's soft and then it becomes stiffer. That's how exponential goes up. So that's the elastic response of the tissue. And then we want to balance that by some tearing energy. So tearing energy is that if we have a crack or a tear and the tear propagates, we get new surface. So tearing energy is the energy for getting new surface. For people who know fracture mechanics, this is like in the energetic framework of Griffith. And then our contribution to the computational model was adding this energy of pressurized fluid. So when we want to model this phenomenon, if we apply the uniform pressure to that cavity, the pressure would go up and then our computational model would fail. But we want the pressure to come back down after that. So we want to control the volume of our injection. So we add this energy of pressurized fluid, kind of in the spirit of hydraulic fracturing in the small strain applications. We control the volume of injection by minimizing our energy with respect to the functions we're solving for, minimizing this energy. And when we minimize that energy, we make the volume that is damaged, which is this integral. So that's the Jacobian of the formation gradient for people who know what that is. So that's the total damage, and we prescribe that volume of injection. So instead of the pressure dropping and computation failing, we can advance time with uniform increase of the volume of injection. And this energy of tear that comes from Griffith type analysis is expressed using an integral form in the phase field model of fracture. And when we minimize this energy, this damage would concentrate around the crack. And we can have a damage field that evolves in our simulation, but it's concentrated in a crack, so we can simulate crack growth. And I implemented this in Phoenix. Phoenix is an open source PDE solver. If, like me, you like Python better than C++, we write some Python codes, a few lines, give it to Phoenix, and it compiles a lot of C++ codes for us, and it can run it over cluster computers. So I have an example of that here, and it's a full example. So if we install Phoenix, we invite it, we make a mesh, we define our boundaries, we have a fixed boundary conditions, we specify our function, and we say that we have trial and test functions, and then we define our weak form, and then we just call a solve function. And it solves here, for example, the diffusion problem for us. The good thing about Phoenix is that we can we can play around with our weak form. So, for example, this flexibility enabled us to model that control of injection volume. So we could play around with the weak form and test it and see what is a good weak form that can reproduce that. So this is a simple equation. To go to like tissue and phase field, it takes a bit more coding, but the functionality is there. So this is an overlay of what our model is like. So if we have an initial cavity and we increase the injection volume, that's what our model looks like. And black would be ink or the damage volume in our simulation, and we increase that. And we can, by tuning the characteristic energy of tearing in our model, we can get a good overlap with the experimental results from Roche that I showed, and reproduce the critical energy that we have, the critical pressure that we have for the tears to propagate. So this gives us some confidence in our model that that probably we made a good model. Now we want to use the model to see how the pressure, like how much is the critical pressure? If I have this aorta, like how much pressure do I need to delaminate its layers? And we know the answer would depend on stiffness, strength, and the size of the initial defect. So I list some historical mathematical development for this problem. From last century, there is research from Snedden that looked at we have an infinite elastic medium and we put pressure in it. This is the formula for how much pressure we need for this crack to open. And then there's work by Gent and Lewandowski that looked at polymer film that is adhered to a glass substrate as shown here. And then we have pressure coming from below the film and trying to debond it from glass. And how much is the pressure that we need to debond the polymer from glass depends on the mechanism of the formation. Sorry. If the formation of the film is more like a beam, or if it's more like a membrane, then we have to use different formulas for elastic energy. And there's a common thread here. The critical pressure that we need for crack or tear to propagate is is somehow related to stiffness and characteristic energy of tearing, or like something like strength with some exponents. So that's a direct relation with like exponent 1/2 and 1/2. And the initial size of defect, or the size of D bond here, or in our problem, size of the initial cavity of defect with some other exponent, and the relation is inverse, as shown here. So when we did our computations and we varied these parameters in our computational model, we saw that the exponents look like this in our computation. So if I increase the stiffness by a factor of 4, my pressure increases by a factor of 2. The same with the strength. And then this is the part that was known to the other communities, like in polymers and in elastic media, but not in biomechanics. We didn't know that there was even an initial cavity, and what was it.